So, as mentioned, I'm Alison and I work with Keelan at the Infant Centre. So we're kind of on the engineering side of things, and we look into a lot of like signal processing, pattern matching, trying to help with diagnosis essentially. And my area is neonatal seizure detection, and I'm using convolutional neural networks and Keras and TensorFlow and everything we talked about last time to actually do that. So let's get started. What I'm probably going to do today is talk to you a little bit about the problem with the detecting seizures, a little bit about the technology I'm using, so CNNs, and then a bit about how I'm actually applying it and how I'm adapting algorithms for this use. So seizure detection in neonates at all stages of life is very important, but in neonates it's very important and it's also very difficult. So when a baby is born, if they suspect that there might be something happening in the brain, they will hook it up to all these different electrodes and try to look at the brain activity. And often the brain activity is the only indicator that there's actually a deep problem in the brain. So this is the first port of call when we're looking to figure out if there is something wrong with the baby. And another reason we want to detect seizures is we actually have some medicines that can be prescribed to treat seizures, but these only work as the seizure is happening, so we can't retrospectively treat the seizures. So it's important that we're able to detect them and that we're able to detect them quickly, so we can tell doctors or nurses that they're actually happening. And when we think of seizures, we think of physical movements, we think of them being, very obvious signs that a seizure is occurring, and that's true usually in adults and in children, but in babies, 2/3 of seizures actually happen at the subclinical level. So that means there's no physical manifestation of them, there's no movement, there's actually no way of seeing a seizure without looking at the EEG signal, so the electroencephalogram signal. That's the only way we can detect a seizure. And then of course you need highly trained specialists to interpret this electroencephalogram signals, and they're not always available 24/7. So some kind of cot-side helper would be really, really great. Something that could sit at the cot-side and look at the EEG signals and interpret them and give some level of probabilistic output of whether something is a seizure or a non-seizure, so that the expert can then be called in to make the diagnosis. So that's kind of the reasoning behind this work and the reasoning behind the development of a seizure detection system. So what you have here is you actually have an example of background EEG and seizure EEG. So you can see on the top, this is background EEG, and what we have is 8 channels. So typically in adults you'd have a lot more channels, but if you think about a baby, their skull is much smaller, we can't fit as many electrodes, so we work with 8 channels. Blue and red indicate different halves of the brain, so the different hemispheres. And what we're really looking for in healthy brain activity in a neonate is randomness. We're looking for no patterns, no repetitiveness. We're looking for pure randomness, because all of these little voltages, these are tiny little voltages, all that they represent are the different neurons firing in the brain. And we really don't want any kind of neurons to be in different loops. If you look at the seizure here, what you see is more ordered rhythmic activity. It's kind of predictable almost. You start to see these spikes happening at discrete intervals, and that's what we don't want to see. So when you're looking for a seizure, you're not looking for anything specific, but in some ways you're looking for kind of order and patterns in randomness. So it's a very strange task. But of course it's not that simple. There's lots of other things happening in these electrodes as well. The electroencephalogram signal is really, really small, so obviously the signal to noise ratio is an issue. And here you can see nice spikes, which seem like ordered pattern, regular patterns, but really what these are is they're the ECG signal after contaminating our EEG signal. So it's actually the heart beat is after contaminating the signal, and that's why we start to see these repetitive spikes, and those are not seizures. Again here, you see these nice little waves, almost like the crest of a wave. That's probably maybe like respiration artifact, or the baby might even just be moving or babbling or feeding. So there's loads of different reasons why we might suspect something is a seizure in the EEG and why it might not actually be. So it's not as simple a task as I make out. So we're really looking for something very non-specific. The challenges of seizure detection is that they can vary in size. They can be large amplitude seizures, small amplitude seizures. They can vary in shape, and they can of course vary in the frequency that they dominate. And they can be in one channel, all channel, or multiple channels. And this is just an interesting example, because what happens here with this seizure, so you can see at the beginning, so this is temporal evolution, you can see at the beginning on one half of the brain, so in the blue signals, we have a seizure, but we have nothing on the red side of the brain, so we have nothing on the opposite side of the brain. But actually over time, the seizure morphs and it moves into the other side of the brain. So this is an example of a seizure moving across the brain, and it's hard to kind of define any clear definition of what a seizure is when it can change its characteristics over time like this. So how does this relate to the CNN, or the image processing challenges, is what I wanted to look at next. Where do we see this kind of variability elsewhere in the data and analytics tasks? So where do we see these kind of characteristics in image processing challenges? So in image processing challenges, often we're trying to look for a class of an image. So we're trying to say this is an image of a dog or a cat or a mountain or a pig or something. So what we have here is we have a small dog, and this is just as much a dog as this larger dog, which is in kind of different colour pattern. It's in grey or black and white instead of in colour. And it's just as much of a dog as this one that's rotated. And it's just as much of a dog as the one at the other side of the screen, where we can only see 50% of the dog, but because we can still see the nose and the tail and the little bit of the ear and the collar, we're like, okay, that's definitely a dog. And even on the right-hand side here, the dog is occluded. It's, you can only see a little bit of it, but we still know that that's a dog. So this is another case where changes in lighting or changes in size or changes in rotation or the characteristics that are present don't change the class of what we're detecting. So in my eyes, this kind of is analogous to the seizure detection task, where we could have a small amplitude seizure or a larger amplitude seizure, or a seizure that's like varying across channels, or even a seizure that's covered, it's occluded because we actually have a respiration artifact happening over it. So it's, it's a bad signal, or even you could have a loose electrode. The electrode could be coming loose, so you have a lot of noise in the signal. So there's kind of a lot of similarity between these two challenges. And one big way that people solve the image processing challenge is through convolutional neural networks. So convolutional neural networks are almost the sole way we do image processing these days. They really came to the fore during the ImageNet challenge. The ImageNet challenge is a challenge that's happened every year kind of in the past decade. And there are 14 million images in the challenge, and there are 1,000 different classes. And you can see that, the error, which is along this axis here, was reducing every year until suddenly 2012, when we saw this 10% drop in error. And what happened in 2012 was Hinton and Krasovsky came up with the AlexNet, and that really changed things. That was the first proper implementation of the CNN, and that's where people started to see the power. And then after that, you have VGG, which is another CNN implementation, and ResNet is 2015 one. And in ResNet 2015, they beat the human benchmark for this processing challenge. So this network is now performing better than humans on this particular image processing challenge. It doesn't mean that they're better than humans on all image processing challenges, but for this one, they've actually outclassed the human benchmark. So we can see that CNNs are very, very good at these tasks where the image can be variable, it can change over time, it can move around in the image. So that's why we thought, why don't we try to use this deep learning and the CNN networks for the EEG seizure detection task. So how do CNNs overcome all these challenges? Well, they have three things. They have local receptive fields, they have shared weights, and they have subsampling, so they have downsampling as well. The local receptive fields are how the CNN knows that if 2 pixels are in a line, or if 3 pixels are in a line, that means there's a line there. Or if 3 pixels are in a triangle, that means there's a triangle there. They're looking for the spatial relationships between things. And it's something that neural networks couldn't really do beforehand. They just looked for what was in the data set, whereas in the CNN, you're actually learning spatial relationships. Shared weights means that you're looking for the same characteristics across the whole image. So it means if you rotate the image, if you turn it upside down, you can still find, let's say, the dog or the cat within that image, because you're looking for your features across the entire image. You're sharing your weights across the full image. And then the subsampling means that, okay, the dog is here on the left-hand side, and the tail can be up high or down low, depending on how the dog is feeling. So the exact position of the features isn't important. We can do this kind of downsampling, which kind of blurs where we're looking for the features. So these are 3 very important things that happen in the CNNs. So local receptive fields are very, very important. As I said, they have a small receptive field which have spatially local patterns. What that means in reality is that if these are image pixels across here, so we have 5 image pixels at the bottom of the screen, and this node here takes information from these 3. And it only looks at those 3, and it learns a very simple representation because it's only looking at 3 pixels at input. And then the next one along, it looks at the next 3. And then the one on the right-hand side looks at these 3. So all of these 3 nodes have looked at very simple amount of data, just 3 pixels of data, and it's learned, whether they're in a line or whether they're in a triangle or whether they're in a horizontal or a vertical line. And that's its receptive field. Its receptive field is 3 wide. And if we go to the next layer, then each of these 3 pixels has learned something interesting about the 3 pixels below it. And this next layer is learning from the following 3 pixels. So it's actually learning something slightly more complex because there's a non-linearity in there, so it can kind of make more of an interesting decision. And you can see that the receptive field, so this pixel here is actually dependent on all 5 of the input. So as we move up the hierarchy, we're getting more and more complex features, but we're still having just those small receptive fields. And how that works is maybe in level 1, we might look for these lines, and lines are very simple, but they're very important. If we're doing edge detection, they're very important. So in layer 1, we might look for these simple lines. But in layer 2, we might look for, do those lines intersect? How do they intersect? What shape does that make? And then in layer 3, we might see, okay, there's 2 sets of lines next to each other. And then as we keep going, we might start to look for really complex things like texture or faces or, other complex things. But it really all starts at these simple, small receptive fields at the input. And how this might relate back to our, looking for dogs task is that this might be the edge of a dog's ear. And then we've actually found, okay, so these 2 together, it's definitely the edge of an ear. And then, there's 2 next to each other, so this is like a German Shepherd with pointy ears. So that might be a characteristic that might tell us, it's a dog. But it could be a cat or it could be mountains. So it's a kind of a transferable feature that we could look for other things with. So that's our local receptive fields, which gives us this spatially local information and which allows us to have these different levels of abstraction, to start with simple characteristics and work up to much more complex ones. The next thing we have shared weights. So this shared weights is what I talked about earlier, where we look for the same feature across the whole image. So if the dog is in the top right-hand corner and the bottom left-hand corner, there's still a dog in that image. We can still say, that class is met. So what happens is we build feature maps of the likelihood of characteristics across an image. So if we have a weight, and that weight is looking for horizontal lines, we look for horizontal lines in the first 3 pixels and give a likelihood of that they're there. The next 3 pixels, a likelihood that they're there, and the next 3 pixels, and a likelihood that they're there. And what we've essentially built up, built up a map of the likelihood of that one feature being in every part of the image. And the important thing to note is that we've actually maintained all the spatial information. So we've maintained whether that line is in the left of the image or the bottom of the image or the top of the image. But we just have this map of the likelihood of that one feature being in the image. And we do this for many, many different ways. So you could do this for 100 different features. And what you do is you build up 100 different maps of the features that are in that layer in the image. So, and they all have spatial information maintained. And usually in the first few layers, these are edge detectors. And then in the subsequent layers, you go on to learn the more complex hierarchical features like we talked about before. So those are our feature maps. And one network that I use in my work is this VGG network. It was developed in Oxford. And it's that network that won the 2014, I think, ImageNet Challenge. And it's really the first network that used very, very small receptive fields. So it's the first network where they really wanted to look at the most basic information at the input. So what you have here is you have an image. It's, maybe downsampled or maybe rescaled in some way, but it's a raw image. No information is taken from it. There's no counting of, the light or the darkness in the image. It's really that raw image. And then what we have is we have 3x3 convolutions in every layer. And in every layer you can see there's a number, so it's conv 64. And the 64 there, or the 128 or the 256, represents how many of those feature maps we extract in each layer. And remember, the feature maps count the number of features that we're looking for in each layer. So in the first layer of this VGG net, we're actually looking for 64 different feature maps. So we're looking at 64 different combinations of 3x3 weights. So there are 9 different values, and we're looking to map those across the entire image. And by the time we get down to the end here, to the 512, we have lots of different feature maps actually extracted, which we probably have lots more complex features extracted, and that's why we need many, many. So the interesting thing about this is that the first, maybe 9 layers are convolutional layers. So they're the ones that extract these features, and they learn what features to extract through the backpropagation algorithm. But then the last 3 layers, so these are FC layers, which means fully connected. So they're the traditional dense neural network layers that have been around for a very, very long time. And what really happens in this kind of an algorithm, in this kind of an architecture, is that the first convolutional layers act as the feature extractors. So they're learned feature extractors. They figure out what they need to learn from the image in order to do their classification task. And then at the end, these last fully connected layers act as the classifiers. So they're the ones that say, okay, well, there was a nose, and there was a collar, and there was ears, and there was a tail. So this is a dog. Or there was a wheel, and there was a road, and there was a door, and there was a person. So that was a car. They're the ones that take all the extracted features and actually make or do a classification or make a decision based on those features. And the interesting thing about the VGGNet and what it's actually very good for is what's called transfer learning. So what we can do is we can take this VGGNet and we can take the first convolutional layers and we can transfer them and use them for a completely different task. And all we have to do is retrain the decision-making layers at the end. So if this was an algorithm that looked for animals, we could also make it an algorithm that decided which movie this scene was from. So you could give it an image from a movie, and if it was able to pick out loads of lions, it would say, the last layers would learn to say, well, that's the Lion King. Or you'd give it an image from a movie, and if it could pick out crabs and fish, it would say, well, that's the Little Mermaid. So we could retrain the network just by looking at the last decision-making layers, because the first few convolutional layers are so good at picking out different features, and we can actually use this as a transfer learning kind of network. So it's very interesting from that perspective. But what am I doing? What does my network look like? And what do I do on a daily basis? So I have used this VGG architecture as the basis of my network, but I've changed it slightly. So VGG is all for image processing. A lot of CNN stuff is for image processing. So it's all 2x2 convolutions, or 2D convolutions, 3x3 convolutions. But remember, I'm working with the EEG. And the cool thing about deep learning is that we don't have to do feature extraction. So what I'm actually using is I'm using the raw EEG signal, which is just a 1D signal. And I'm putting that in. So you can see here, I have 8 seconds of EEG. That's what it would look like. At the input, it's sampled at 32 hertz. So I have 256 samples of raw EEG at the input. I essentially have a 1D vector here. And what you can see is the hierarchical feature extraction happening. In the first set of feature maps, so in the first layer, I'm just looking at 3 samples from my raw 256 long vector, and I'm learning something from those. I could be learning lines, I could be learning flat, I could be learning, anything from those. And then in the next layer, I'm looking at, again, three samples from here, so my receptive field has moved up to the 4, because I only have a shift of 1. And then I'm learning a little bit more there. So what I'm doing is I'm not actually telling the network what to extract from EEG. I'm not telling it to look for repetitiveness. I'm not telling it to look for order. I'm not telling it to look for entropy. Instead, I'm just giving it the raw EEG, and it's figuring out what it should be learning, what type of filters it should be applying to this raw EEG. And the whole thing is temporal. So you can see that the features up here still maintain their temporal relationship. So the most left-hand feature over here is actually related to the most left-hand section of the EEG over here, which is very interesting, and it allows us to make some kind of connection back to decisions at the end. We'll talk about that later. But what you might notice is very different between this and the VGG that I showed you is that I don't actually have any fully connected layers. So often in image processing, you have huge amounts of data in one image. Maybe your image is 255 by 255, so that's a lot of data. But I only have a 1D signal, which is 256 samples long. So I don't have that much data. And we all know in deep learning, or not in deep learning, in all machine learning, overfitting is a problem. So instead of actually using densely connected layers at the end, which introduce a huge amount of parameters, I'm actually using kind of a way to manipulate the end of my network into creating 2 different feature maps, one representing seizure and one representing non-seizure. So you can see I have lots of filters in each layer, this number of filters, lots of filters. And then in the very, very last layer, I'm just using 2 filters. I'm creating 2 feature maps. Essentially, I'm doing that scanning across the entire image with just 2 features. And those features, one is looking for the seizure, and it's scanning for seizures, and one is looking for non-seizures, and it's scanning for non-seizures. And then I'm taking the 2 values that come out of that scanning, and I'm saying that, okay, they're my probabilities of being seizure and my probability of being non-seizure. so I can do some kind of a softmax function to make them into the probabilistic values then. So this helps me to avoid overfitting, and it allows me to have two feature maps at the end where one actually represents the location of seizure-like data in the image, and one represents, or not in the image, in the signal, and the other represents the location of non-seizure-like data in the signal. So this actually can be quite helpful from a clinical perspective. So it's based on the VGG network. There are 1D convolutions only, and there's no dense layers used. So how do we overcome these seizure problems that we talked about earlier? The local receptive fields mean that we're actually looking at temporal information in the EEG signal. So the EEG is a temporal signal, and because we have locally connected weights, that means that the spatial relationship is important. And because it's a temporal signal, the spatial relationship actually means temporal relationship. So that's helping us there. Those local perceptive fields are helping us learn some little bit of temporal information. Shared weights means that even though seizures can vary a lot and they could be, in lots of different positions, it means we're looking for the same weights across the entire EEG signal. And the subsample means we're not looking for one set exact feature kind of pattern. Instead, we can look for kind of a little bit of a wider variety of patterns. And how does this compare to shallow learning? Well, the thing is, there's some really, really good seizure detection algorithms that exist out there that are based on like very, very powerful machine learning classifiers, like SVM, decision trees. There's loads of different types out there. And what they do is they have this pre-processing stage where we look at the EEG and we downsample it, and then they have feature extraction. So the feature extraction is where they actually look for all those things we talked about earlier. They looked for the different frequencies in the seizures or in the EEG. They look for the number of spikes in a minute. They look for the entropy of the signal. And because we know that all those things help us make a decision, help clinicians or help doctors make a decision about the seizures. So they use this kind of human engineered information to create these features that they're extracted. And then they use the machine learning classifier, and then there's a post-processing step. And really what we're doing with this deep learning is we're actually replacing both of these blocks with one classifier. So we can actually replace both the feature extraction stage and the classification and the decision-making stage with one classifier. In that VGG net, it was like the convolutional layers were the feature extractions, and then the dense layers were the classifier. But the cool thing is that this whole section is now optimized in one routine. So rather than optimizing the features for the specific task and then optimizing the classifier based on those features, we're optimizing the entire thing end to end, which is a much more valuable thing to do. So this is kind of the comparison between shallow learning routines. But of course, a lot more kind of intelligent and really good work goes into these things, because they have to decide what features to extract, and there's a lot more decisions made there. But we just did a performance analysis between one of the best seizure detection algorithms for neonatal EEG and this convolutional network. So this is an SVM-based system. It has a lot of parameters, and ours doesn't have as many because we didn't use any dense layers, so it's quite the number of parameters in our network is very restricted. The AUC, so the area under the receiver operating curve, so the analysis of sensitivity versus specificity, theirs was 96.5%, which is really, really good, and ours was 97.62, which just kind of outdid it by 1%, but really at that point 1% is a big increase. And then the sensitivity at 1 false detection per hour. So this is the actual sensitivity of the network when we allow it to make 1 false detection per hour. Because if you think about clinical context, you don't want the alarm to be going off every 5 seconds because it thinks everything's a seizure. We have to reduce the amount of times that the alarm goes off by mistake. So they were getting 88% for this sensitivity at 1 false detection per hour. We were just getting 89%. So you can see that even without all that really, really intelligent, highly engineered feature extraction, we were able to make something that was very comparable and actually kind of outclassed it in a few of these metrics. And I talked about there the fact that the final 2 feature maps were a representation of the seizure and non-seizure elements of the input. So what I have here is I have a very long input. It's a minute of input. Usually you wouldn't have a minute, but the fact that we don't have any fully connected layers, you can actually vary the input as much as you want. You can put as large of an input as you want or as small of an input as you want, because there's no hard-coded weights. All the weights convolve across the image. So that's actually another kind of interesting thing you can do if you don't have any dense layers. But what happened here is this 1 minute of EEG was put into, it's actually a seizure EEG, was put into the algorithm, and the last two feature maps I'm plotting here. So the last two feature maps are the ones that I told you we kind of manipulated to make them represent a non-seizure and a seizure epoch map, or feature map, sorry. So this is the non-seizure feature map, so it's very unlikely that it would be non-seizure, that the average is very, very low, the values are very, very low. Whereas this is the seizure feature map, and this is the one that's trying to detect what is a seizure characteristic. So you can see here that this is very, very high. And the interesting thing is that we can actually, because the temporal relationship is maintained throughout the entire network, we have no fully connected layers, so we have this maintained temporal relationship. We can actually say, okay, you know, where were the most seizure-like parts, and what did they relate back to in the input? So what we can say is, well, here we had like a very high average for a few seconds, and we can say it related back to this part of the input. So that might give us some insight into, you know, different clinical uses for a network like this. But there's always problems. So the first thing you might say to me is, it's a black box. Do you really know what's going on? When we extract features, you know, we're learning a lot about a signal, where we know what's happening, we know what we're looking for, but why does this do so well? And that's really important, and that's why it's important to, you know, try to analyze your networks. And people are talking about visualizing different parts of their layers and different parts of their convolutional neural networks, and it's something really to bear in mind when you are developing like a neural network or a deep learning approach, because, you know, we can just kind of do it blindly and not think about what's happening inside. Another thing is, can we go deeper? And that's a great question, and I would like to explore that and see if we can, you know, get even better results by making a deeper or more complex network. Because, you know, as I said, the deeper you go with your layers, the more complex the hierarchy of features you're extracting. And then the other thing is that transfer learning I was talking about. So we said that in images we can, you know, use the same convolutional layers that were learned that extracted a certain amount of features, and we can use them for other image processing tasks. But is there a way that we can use these kind of EEG features that are being extracted for other EEG processing tasks, maybe where you want to detect sleep cycles, or you want to detect, you know, different you know, types of brainwaves? And that's also something that would be really interesting to explore, I think, in future. But that's everything I have for you today, so thanks very much. I'd love to take questions.
Just when it comes to there, is there any choice in picking what features are picked out? Because it might have a statistical importance, but not a practical importance. So
yeah.
Statistically, it might actually be important, but practically it's not.
That's the thing, like, you know, you're putting in something raw and you're letting the network decide what is extracted, and that's actually one of the drawbacks, because, as you say, you know, there might be some value in knowing what features are good and what features are bad. You know, there might be a lot of value in learning about that, but I don't know of any way to manipulate what features would be extracted, unless, of course, you did some kind of feature extraction stage beforehand and got a value for that and put that value in as part of your input. So, you know, use that value as an input feature almost. So I'm not doing any feature extraction, but maybe you could do some feature extraction and extract one value. I don't know what it would be. Like, let's say here it would be the frequency in the lowest subband, the 0 to 2 hertz subband, and put in the signal, which is the EEG signal, and also put in that frequency at some point in the network, you know, concatenated at some point in the network. That would be the only way I would know. But I don't know. Sorry.
So, nice talk. Thank you very much. On the EEG signal, so you have a time series. Is it important that that time series is contiguous as the inputs to the net? They're connected, so, you know, each millisecond is next to each millisecond relates to the first layer of input, or are they completely randomly?
During training, definitely they're completely randomly inputted into the network. So like
one from 10 minutes,
yeah,
10 seconds
yeah,
could be next to one from
exactly, because no information is maintained historically. So every time I present something new to this network, a new 8 seconds to this network, it doesn't remember the last 8 seconds I presented. There is no kind of recurrent, there's no actual like temporal learning. That would be more kind of LSTM or recurrent neural network. So it would be long-term, short-term memory network or a recurrent neural network, where, as you say, the last information would have some significant value on, or not even some input on the next information, where if the last second was a seizure, well, surely you could take some information and say the next second is probably a seizure. But I don't have that in this network at all. No, that's a little bit more complex network.
And do you think that's an advantage, or Because I mean, obviously, what you're doing is you're randomly sampling the signal. So you're saying I'm going to start with a completely open mind.
Exactly.
It might be there's something that happens in event 3 seconds that has an impact on event 8 seconds.
Yeah. I definitely think that kind of temporal information and helping the network by giving it some history would probably help, but I haven't done it yet. But I do think there would be an advantage to that. But then if we also think about during training, you don't want to present it with loads and loads of seizure epochs in a row, because it might, if you think about your local minimum plot, it might sit in this local minimum where it says everything is a seizure or everything is a non-seizure. So I think it's important during training to do, like, when you're training something like this that doesn't have any historical context, to do very randomized training, to not train it on loads of seizure stuff in a row or loads of non-seizure stuff in a row.
I've probably got a similar question. It's just, I always associate convolutional with imaging. So
Yeah.
are you actually processing this as an image? Are you taking an image as opposed to a signal?
It is a signal in that it's a 1D vector.
Okay.
But there's no real difference between a 2D vector and an image, really, is there, if you think
Okay.
about it?
Okay.
So
I'm just intrigued because, and again, it's a new field, so recurrent neural networks is something I would have thought would be the
perfect
the
for
natural.
signal.
Exactly.
Yeah.
But it's interesting. You're going.
This has got it's interesting that this has gone well, but the reason actually there's like a thing how I ended up doing this, but I was looking at the 8-second epochs of EEG represented as spectrograms.
Okay.
And so then the obvious thing to do would be to use convolutional neural networks.
Okay.
And then we kind of thought, okay, well, the spectrograms weren't representing all the data. The second you create a spectrogram, you're actually losing some of the information that's in the EEG. So we said, what if we just go to raw EEG and put that into the CNN? And so I can see how it doesn't make sense that I've gone from signal to something that's not LSTM or not temporal. But it has worked, and I think it has worked because we've kept it potentially as a temporal signal. So there is some small temporal relationship within the 8 seconds, but there is no historical connection to the previous 8 seconds.
And you're doing epochs at 8 seconds, and then you're labeling that as this is a fine, this is fine, this is a seizure.
Yeah, and then some post-processing after that. So this isn't instantaneously done right now. It's not actually kind of streaming online right now. It's all done retrospectively. So we can do some post-processing and manipulation and moving average filters after that to help. But there's that as well. I'm just going to
against any other types of algorithms, or
no other deep algorithms. I haven't tested against other deep algorithms, but you can see the SVM algorithm, which is a machine learning algorithm more than anything.
and one quick one, dynamic time warping. Have you tried that?
That would be very interesting, and I haven't, but that would be very interesting.
Yeah.
Yeah, very, very interesting to look at. Sorry, who was first there? Or anyone?
I was just wondering, since your sort of EEG displays show multiple channels of information, like for the left and right side of the brain, have you done any work on combining multiple signals?
I have done a little bit of work on that, yeah, but I think the issue, but I haven't done anything that's been fantastic yet. I'm working on it, but I think the interesting thing about that is, so I order them as 1, 2, 3, 4, 5, 6, 7, 8. But really there is no actual order to those 8 because they come from all different parts of the brain. They're kind of spatially, in 2D way they're represented, rather than 1 is related to 2 is related to 3. So it would be important if I did do that, if I did look at them as all 8 together, that I wouldn't have probably shared connections between the channels, that the connections would only be within the channels, because I can't say that the relationship between 4 and 5 is the same as the relationship between 1 and 2. But yeah, that's a good thing to pick up on. Yeah, very interesting.
That was one thing I was going to ask. The other was, is there a particular reason for 8 seconds? Could you just pick longer? Or? No,
there's no particular reason for 8 seconds, and I've been looking at longer, and longer actually seems to be doing better. But the interesting thing about this architecture that I mentioned is that even though it's trained on 8 seconds, we can use it on 16, 32, 64 second inputs because there's no fully connected layer, which means that there's no, temporal, there's no weights that are hard coded, so all the weights are convolving. So I've been using networks trained on 16 or networks trained on 4 seconds. I'm currently trying to do some larger experiments where I'm training it on 1 and testing it on another, so kind of mismatched conditions to see if I can get anything out of that, but it's another big project. Good question. Pardon?
Are you doing any overlapping on your windows?
Yes, actually 7-second overlap, so it's 8 shift 1 second. So I'm getting as much data as possible, because with neural networks, probably the more data the better.
Yeah.
So if you think about the fact that, and I can't, so Keelan talked about, warping images and changing images and creating more data out of that.
Yes.
But with this, it's, I think I would have to have someone with clinical context sit next to me and say, okay, if I warped this seizure, does it still look like a seizure? Because I don't know if that is still a seizure. So one way I can create data and make as much data as possible is by having as much of an overlap as possible.
Okay.
Because in theory, that's making more data.
Yeah.
It's kind of a way of making more data without knowing much about the field or
Yeah.
without being an expert in the field.
Sorry, just 2 quick questions. Are you getting are you doing live tests yet, or is it still recorded data?
It's still on recorded data, yeah.
Are you looking at something that's extremely rare or something extremely common?
Extremely rare. This is a massively imbalanced problem. It's probably, if I have, and all of the data that I have are actually patients who have suffered from seizures. So, but still only about maybe 6% of my data is seizure data. So it is imbalanced. But during training, that's one thing with neural networks. During training, I'm balancing it. So during training, I'm taking, okay, I have this much seizure data. I'm going to take, twice as much non-seizure data, but I'm not going to use all of the non-seizure data because otherwise I'm going to end up with something that's not training very well. So I'm kind of balancing the data during training.
So you're scoring it using an ROC or UC then? Or?
Yeah.
Okay. And that's okay for class imbalance? Or?
Yes, it's probably better for class imbalance than accuracy, but yeah.
Okay. I was wondering, did you look at F1 macro or?
No, I haven't, and probably is better for class imbalance, but I haven't because the metrics I was comparing to when I started these experiments were those.
Yes.
I just started comparing, but yes, for a better or maybe a slightly more robust metrics to look at, it would be interesting to look at that.
I know it's a real bugger because you're trying to compare it and then someone else is using accuracy figure.
Exactly. You're trying to match the kind of historical thing, but yeah.
You can't apples and pears comparisons, yeah. Okay.
I'll be around anyway if anyone wants to say anything else. If I'll let Peter go.
Great stuff. So, great talk, Alison. Thank you very much indeed for that.